All right, welcome back to Print Reading for Welders. My name is Evan Radulescu. I'm one of the welding instructors here at Counterbored College. Today we're going to go over Unit 4 of our textbook, and it is dimensions. Now, what are dimensions? Well, any measurement you have is going to have a quantifier and a qualifier. If I say something is 4 feet, you understand 4 feet. But if I say something is just 4, you don't know what that is. Is 7 a lot? 7 chicken nuggets? Not too much. 7 dead bodies? That's a lot. So you need a quantifier to understand whatever that number is representing. 4 inches, 4 feet, 4 miles. These are all very different things. So that is a dimension, whether it be angle, whether it be length. There are going to be different dimensions, all right? We're going to be talking about tolerances within welds for how accurately you need to build the part. And we're going to identify some of the elements of minimum and maximum whenever it comes to tolerances. And we're going to go over the importance of a scale of a drawing. Not everything is to scale, or how it is being scaled. If on the print, if it looks one size, it may be 4 times that size in real life. Because prints that are actually the size of a trailer, that's not very useful. You're going to have a print on a regular sheet of paper that's a size B scale, and the trailer is going to be scaled down on the drawing. So you'll know anytime you draw a measurement from that trailer or from that piece of paper, it's actually going to be much larger in real life. All right. We're going to go over, so there's 2 types of common dimensioning. We have conventional dimensioning and baseline dimensioning. In conventional dimensioning, each measurement is drawn out each time. So if you go from one end of the part to the other, you have 1 inch, and then they measure from there another 1 3/8, and then from there you can measure out 5/8, even if they're stacked on top of each other. So for conventional dimensioning off of this, you'd measure from here to here, you have 1 inch, and you'd measure from that point to the next point, and that'd be 3 inches. So each time it builds off of each other. If you were to measure across this part, or if you were to be measuring these holes across, it would measure from here to this part of the hole, then from that hole to, from this side of the hole to this side of the hole, then from here to here, then from here to here, and then here to here. That'd be conventional dimensioning, and you'd have a measurement for each one, and you'd have an overall length. Baseline dimensioning, and with conventional dimensioning, you are using fractional inches whenever they call out the sizes. So it'd be 1, 1 1/4, 1 1/2, whenever they'd give you those measurements. Baseline dimensioning is is a little bit more precise, because you're measuring everything from this point right here. So if I wanted to know these locations of these holes, I'd start from here and I'd pull my measurement here. So I'd go 1 1/2. And then for the start of this hole over here, I'd measure again from this point, and that'd be 3 inches. So everything's drawn from a baseline. So conventional dimensioning builds off of each other, while baseline starts from a single point. The other important aspect of common baseline dimensioning is you'll use decimal inches instead of fractional inches. So you'll be having, instead of 1 1/2 inches, it would say 1.5 inches. Instead of 1 1/4, it would say 1.25 inches instead. Baseline's usually used more for machinists in the real world, while most weldments will use conventional dimensioning. But baseline dimensioning I consider to be far more accurate than conventional dimensioning, because with conventional dimensioning, you can take this measurement, move on, take the next one, move on, take the next one, move on. Across this whole part, you took 4 separate measurements from 4 different points, and if you have a slight error in each measurement, over time that error will build up in a cumulative error. Baseline dimensioning, you're always drawing from one point, so it'll be a lot more precise. You have a less chance to introduce error into your measurements or whenever you're building something. Now, dimensions, they serve 2 purposes. They give the size needed to fabricate the part, And they'll also indicate the location of where components should be for that part, where they should be placed, where they should be assembled, machined, or welded. Dimensions will let me know if I'm putting a weld here. Dimensions let me know where I should put the holes on this piece. If I didn't have those, I wouldn't know where this needed to go. An engineer is not going to wave their hand at a part and say, oh, I need 2 holes in this part somewhere in the middle. No, they're going to tell you exactly where they want them through dimensioning, okay? Now, we use both customary and metrics units whenever we use dual dimensioning, but around here we use mostly customary, US customary dimensions, so inches, fractional inches, and decimal inches. There are prints that will be called dual dimensioning where they will have metric measurements on them, but you won't run into them too much. Now, US customary linear dimensions are given as whole numbers, so 1, 2, 3, 4, these are all whole numbers. Fractions, 5/8, 3/4, and decimal fractions, 0.5 inches, 0.25 inches. The preferred practice is to show decimals, but on most welding prints, you're going to have fractional inches because what you're going to be using when building large structures is a tape measure, and tape measures have fractional inches on them, generally not decimal inches. You can convert fractional inches to decimals. It's very simple to do that. Fractional dimensions are used for welding drawings, and then the dimensional inches or the decimal dimensions will be used for machining operations. If you're a machinist, you're going to use decimals because it is much more precise. Common fractions that we have 1/2, 1/4, 1/8, 1/16, 1/32. This is what you'll be seeing on most US customary dimensions. Now, a fraction is just a whole that's split into separate pieces. It's if you imagine you have a pie and you split it into certain pieces, you get a fraction of that pie. So a fraction is going to be represented by a numerator and a denominator. The numerator is on top, the denominator is on bottom. The bottom, or the denominator, is what will tell you what you are dividing that whole by. So here's my pie. I've split it into quarters, all right? Now, if I'm going to take those 2 parts of it, I'm going to have 2 quarters. Now, this can be reduced down to only 1/2, but because you can see I've taken away half of the whole, but I've split this into 4. And that's why I have my 4 on the bottom, but even though you can, I took 2 parts of it away, you have now split this into 2 pieces, so your 2 shows you how many parts the whole has been split apart. If I were to take this and I've split the whole into 1/8 now, all right? So I have 8 pieces that make a whole, so that's my denominator, but I only have 5 pieces that are shaded in, so I have 5/8, all right? This is taking a whole number, 1, 2, 3, 4, and splitting into the fractions. So that's just telling me how much of a whole that's got split up, and this is telling me how much of that whole that I have, all right? Addition and subtraction of fractions, very simple. I've gone over that in another video. Current practices are to use unidirectional dimensioning system and decimal fraction dimensions used when precision is required. Unidirectional dimensioning, it's pretty simple to understand. It just means you read the dimensions both ways, all right? If you measure this out and it's 4 inches that way, means it'll be 4 inches this way as well, all right? On this slide, you'll see we have several sizes, and those are marked out. So the size, you have two types of dimensions. You have size and location. So a size dimension is going to be how large the part is, and then a location dimension is going to let you know where certain features of that part are. So for here, if we put a center line in this hole and a center line in this hole, those dimensions would be location dimensions for where these holes should be, while a size or shape dimension would be for the size and shape of the part as a whole. Usually we're preferred to use fractional inches, and we will like to read them from the bottom of the drawing. So if they're drawn out and you're given size dimensions, usually the sizes are going to be on the bottom or on the side, but they are not going to try and put the size of the part above it. They're going to try to put them below it. Angular dimensions, when a line is at an angle to a horizontal, vertical, or angular line, included angle is shown in degrees. Angular dimensions are sometimes shown in degrees and minutes. Decimal degrees are preferred. As you can see on this slide here, an angular line to a vertical line, the included angle is 30 degrees. So what's that measuring is from the 0 on the bottom up like that, and then the space between that would be our angle, or our 30 degrees. And with each degree for a whole circle, you have 360 degrees. If you go a flat is 180 degrees because it's half the circle. 90 would be a right angle. And within each of those degrees, you have 60 minutes. So 1 degree can be split into 6 individual pieces, and it would be 60 minutes. Now, a minute of angle is what it's normally referred to as, is so precise that if you were to measure it out at 100 yards, a minute at angle would move the point from there 1 inch, all right? So while a degree would move it 60 times that amount, 1 degree over 100 yards would be 60 inches. 1 minute of angle is only 1 inch over 100 yards. That's how precise a minute of angle is. Usually we will use decimal degrees. So if I had 60.5 degrees, I would write it out that way instead of 60 degrees in 30 minutes. A bevel is a sloping edge that extends fully or partially the length of an edge. And then the sharp edge formed at the end of a bevel is commonly called a feathered edge. And if you were to flatten that edge, it would be the root face. It's the area along the edge, often called a land. So if you hear somebody referring to a land on a piece of pipe or a beveled edge, they're talking about flattening that feathered edge to give you a certain size land. A chamfer is often identified and treated as a bevel, but the main difference between a bevel and a chamfer is that a bevel will be welded on later, or it will have weld added to it, and a chamfer will not. A chamfer will be left alone and will have no weld added to it. Here you can see a bevel that was made, and you can see the marking. We have our land, and it is marked as the root face, and you can get a measurement for that. And then the bevel is measured as a 3/8 bevel from one end down there at 45 degrees. So whenever I dimension that out, I'm measuring from one point to the other point there to the end. And it's going to be at a 45-degree angle. Beveled featured dimensions with a note and a leader. Amount of bevel given has a linear and a degree dimensions, and bevels may be dimensioned using extension and dimension lines. Sizes given has 2 linear dimensions, or as 1 linear dimension and 1 angular dimension. The use of dimension lines is usually far more accurate and easier to read, but the use of a leader line and a note gives less clutter to the print and makes it not necessarily easier to read, but it makes the print look better. But the dimension line method is far more accurate, in my opinion, and far easier to understand. You can see right here, I have one using the dimensioning line method and the other using the note method. Several dimensionings are for curves, radius, and arcs, angular dimensions and radius, 2 linear dimensions and a radius, radius and center lines, and then there are arcs with multiple radii, or radius. Dimensions shown are location for radii and size of the radii. So here, whenever you're measuring a radius, that R1 measurement is your radius, and then the measurement above it is how many degrees that radius will go. And you can see we have an off-center radius on figure 4.8 here, where they dimensioned it out with dimension lines and then gave you a radius to work off of from that dimension line. And that will be an arc that you follow. Now the other arc at the bottom there has 2 separate radius, and it has a center line showing you where it drops down to and where the origin of each radius is, but it's a curving arc that changes directions. Drilled holes will be shown by a leader and a note applied to the view that shows the shape of the hole. The notes give size of drill, number of holes to be drilled, or depth of drills. Holes with no depth dimensions drilled all the way through may also be indicated by adding the word through to the drill size dimension. For the holes, if you get a location for a hole and it says it wants a 1/2 inch hole on this and it gives you no other information, just assume that that hole is drilled all the way through. Some holes may have depth dimensions where you do not drill all the way through. That would be called a blind hole because they do not go all the way through the material, but that will be included in a note and the dimensioning. Now in figure 4.10, you can see here that they've dimensioned the center lines of these holes, and they've used a conventional dimensioning method because it is based off of each other. And then each hole has a leader going to it, and within that note, it lets you know how big of a drill it needs to be or how large the hole needs to be. And then it tells you the depth of the cut on some of them, and then the ones without a depth of cut, you can assume you're going to drill all the way through. Now, countersunk, counterbored holes, and Spotface dimensions. Abbreviation DP or symbol for depth applied to a counterbored hole dimensioned. Depth of Spotface hole is not given. Depth of a countersunk hole is not given as well, because they will only go as far as needed for the screw or bolt to sit flush. Major diameter of a countersink is provided, while dimensions for flame cut holes are followed by the word flame cut or FC. So if a hole is to be drilled, it will include that information drilled, and if a hole is to be flame cut, you'll see FC or flame cut in that note as well to let you know how that hole is to be made. On figure 4.11, you can see the difference here between a counterbored hole and the symbol for it, and the countersunk hole symbol. If you notice, a counterbored hole is straight walled or a bored hole with a smaller hole through it for which a bolt can go into it, while the countersunk hole has an angled space for the head of a screw to fit in it. Countersunk screws would fit flush on that for the appropriate sizing. Spotface hole symbol is the same as the counterbored symbol, but it will have the abbreviation SF to indicate Spotface, all right? And then a counter drilled hole is abbreviated CD or C drill for counter drill, while the abbreviation for countersunk is CSK. There isn't a symbol for the counter drilled hole, but there is a symbol for the countersunk hole. You will also get a dimension for how deep to drill that counter drilled hole. As you can see here on figure 4.13, it is conventionally dimensioned and is giving you off the center line for where these holes are to be drilled. And then each note is letting you know how far to drill, or the size of the drill hole, and then the angle of the countersink. And it's giving you the diameter of how large that countersink needs to be. And then it will only go as deep as it needs to go for the diameter of that countersink to be 3/4 of an inch, while the drill depth or the drill size itself or the hole size is 1/2 an inch. On here you can see the current method where it's using 0.500 for the hole for the current hole or for the through hole, and then 0.750 for the surface face or the spot face. So that SF would be a spot face hole, and it's telling you 2 holes, so that instead of having a line pointing to each of the holes individually, you just know that the one next to it, because there's 2 of them, will also be prepared a similar method. Now the view on these drawings as well are showing you a front view and then a side view, so you can actually look through the part and see what's being drilled into. Now, notice the use of decimal inch with most drilled holes. 0.003 will have 3 decimal places. So any decimal inch you run into is usually going to have 3 decimal places, all right? Now this can be read as thousandths of an inch because we go from the 10 to the hundredths to the thousandths, all right? So 0.750 can be read as 750 thou, or 750 thousandths of an inch. If you ever hear me use the word thou, I'm talking about thousandths of an inch, all right? But 750 thou is also 3/4 of an inch. Here they have on 4.15 2 counter drilled holes, and the way they're dimensioned from the previous method above using fractional and decimal, and then below they're denoted with only decimal inches. Tolerance dimensions. They're a figure given as a plus or a minus quantity that allows for a variation in the dimensions. If you're building a part, sometimes you're not going to get them exactly right each time. If you're building 100 of these, you may not get it the exact size every time, but the tolerances allow for a little bit of mistake. It specifies the permitted amount of air. Any or all dimensions on a print can be given a tolerance. A drill hole tolerance is generally going to have a tighter tolerances than an overall dimension size. I need these holes to be 1/2 an inch in size, and I want that within 10 thousandths of an inch, but their location can be off by, say, plus or minus a 1/16 of an inch. Tolerances follow the dimensions to which it refers normally. And you can also find our tolerances in the title block. You can be given as a note or a specification. Tolerances are going to ensure accuracy and proper fit of parts, and the tolerances are standardized for many parts found in tolerance tables. So if it's a part that your company builds on a regular basis, you're going to have a tolerance table off to the side, or you're just going to know what the tolerance needs to be for that part individually. If no tolerances are given, you can assume a tolerance of 1/64 for fractional dimensions. So if it's telling you to build a table that's 49.5 inches long, it wants you to get that with plus or minus 1/64 of an inch. If a tolerance is dimensioned for decimal fractions, you can assume 0.010 shown to 2 decimal places, all right? So 10 thousandths of an inch. A tolerance of 0.005 for decimal fractions shown to 3 decimal places. So if they show you a decimal fraction that goes to 2 places, you can assume 10 thousandths of an inch. If they show you a decimal fraction that goes to 3 decimal places, you can assume 5 thousandths of an inch for tolerances. Now, dimensions may be full, enlarged, or reduced scale. Reduced scale sizes are more commonly used on prints. Again, if I'm building a trailer that's 20 feet long, I don't want to have 20-foot long blueprints showing me how to build it. So I'm going to reduce that scale down to like a 1/20th scale. So a 20-foot trailer would fit onto a 20-inch piece of paper, and that would reduce it down by 12. So if I use 12:1, I'm converting 1 foot down to 1 inch on a print. It's a very useful scale to have, because if I need to find a dimension that I don't have written on there, I can use a ruler or a tape measure if a print is to scale. And if I measure a part out that looks to be 3 inches on the print, I'll know it'd be 3 feet in real life. While an large scale drawing is often not as used as often, it is useful for showing detailed components. Things that would have in large scales would be microprocessors or computer chips, because those need to be blown up, because in real life they're going to be so small it'll be hard to see with the naked eye. But if you need to know the pathways for what you're building into it, you need to blow it up and increase the scale. Machinists will use in large scales on things like hub axles or anything else that requires a lot of precision measurements. They'll enlarge the print details so that they can see smaller parts of it and more intricate pieces. If you ever seen a mechanical watch or the inside of it, all the gears and machine work that go inside of it will be on a large scale on the print, so you can see the detail of each one, because in real life, while it may appear to be 5 inches on a print, in real life it may be 5/16 of an inch. It may be a fraction of an inch that size in real life. Scale size allows for a direct proportion to actual size, and it's going to be listed in the form of an equation. So reduced scales are going to be fractional, while enlarged scales are going to be multiplicative. So for a reduced scale, it's going to show as 1 divided by 4 or 1 divided by 10, depending on the scale, while an enlarged scale would say 4 to 1. So it would be 4 times the actual size. Standard thread symbols are used on prints to represent threaded parts. Thread dimensions used using a leader followed by a thread specification. Left-handed threads will be denoted by a LH following the class of fit specification. Common V-thread forms, just go over those real quick. We have national coarse, national fine. We have unified national coarse and unified national fine. These are the super common V-form threads that most bolts and screws are made out of. There are millions of different thread patterns out there. There's Acme style threads, there's trapezoidal style threads, there's just all different forms of threads that exist. It would take you a decade to memorize them all. Don't even try. Just reference them in a book if you run into one that's something you don't recognize. And usually as a welder, you will not be cutting threads. You may use a tap and die to cut threads, but you will leave the other more eccentric threads to machinists, because they'll be the ones making those on a lathe. Here you can see we've got an external thread symbol, the conventional versus the simplified. We've gone to more of the simplified use because it is easier to draw out and it makes less cluttered on the print. And then we have an internal thread symbol. So whenever I say external thread, think of a bolt. And if I say internal thread, think of what the hole that a bolt goes into, all right? That's all it is, internal thread versus external thread. Internal threads will be drilled holes with threads inside of them. External threads will be the bolts that go into them. On here you can see an internal thread symbol for a sectioned view. So how the thread is going to be normally denoted, we'll have 3/4. Starting off here on figure 4.20 is 3/4 is the diameter of the thread itself. 10 is the number of threads per inch. So for every inch of that part, there will be 10 curls or 10 circles of threads, all right? And that's going to be from peak to peak on those threads. Then you'll have the thread form. In this case, it's UNC, or Unified National Course. And then 3 is going to denote the class of fit. I believe there's 3 classes of fit, 1, 3, and 5. Each class of fit is the tolerance or how well it's going to fit with the other part. High tolerance parts are going to have higher levels of fit, while lower tolerances parts are going to have more slop in them. It'll be more loosely connected, and they'll have a lower class of fit. In this case, we have LH at the end, which is the direction of the thread, or a left-handed thread, or a reverse thread, all right? If a thread doesn't include that at the end, you can assume it's a traditional thread, where if you turn it to the right, it'll tighten it or push it in. And then if you turn it to the left, it'll loosen the bolt and remove it. That is a traditional fit. Now a left-handed thread, if you turn it to the right, it'll loosen it, and if you turn it to the left, it'll tighten it, or a reverse thread. Now, conventional dimensioning is the overall dimension, length, and width and height given. Reference dimensions given by adding or subtracting other dimensions on the drawing facilitates reading of the drawing. If overall size is not given, dimensions added to find the overall size. Decimal dimensioning is preferred. So here, again, we've got the conventional dimensioning method, and you can add all those together, and you'll get your overall length. And at the very end there, you can see that's a reference dimension. If it has enclosed in parentheses, it's going to be a reference dimension, because they got that by adding our 1 and our 1 3/8 together and subtracting it from 3. So you're left over with 5/8. Now, baseline dimensioning, all dimensions originate from the baseline. Dimensions are normally expressed as 3 place decimals. Baseline object lines that are usually represent machined surfaces may also originate from center lines. Calculations are not required to find any dimensions with baseline dimensions. They are commonly used to dimension precision parts. Here you can see they use a baseline horizontal dimension and then baseline vertical dimensions on figure 4.22 here. And notice the use of decimal inches and not fractional inches. All right, basic size or base size of a part to which a tolerance value is applies. Actual size, size of a part when measured, and nominal size, dimensions that represent an approximate size. If you build a bunch of different objects and you go out and measure them, that measured size will be the actual size. And then a nominal size would be if you order a 20-foot piece of bar stock and you get a little bit more than 20 feet, it's because they sell them as nominal size. It may be a 1/4 inch longer, it may be an 1/8 of an inch longer, so you don't know whenever you order several structural beams if they're all the same length. They will probably all have to be cut to the exact size that you need because they are brought to you and called a nominal size. If you go to the hardware store and buy 2x4s that are 12 feet long, they may be a little bit longer, so you need to measure those because they are sold as nominal size. If you buy a 4-foot by 8-foot sheet of metal, it may be a little bit larger than that because, again, you order that as nominal size. Anytime you buy material or it is sold as nominal size. To know what the size of the piece that you're actually working with, you have to actually go and measure it to get the actual size. Here you can see a reference for a basic size dimension, and they've got a tolerance there as well. Limit of size, dimensions that indicate upper and lower limits, and call out, it's an identification of each parts by means of numbers. So each individual part could be labeled with a number, so 1, 2, 3, 4 for a part that's being built, or it could also be given a letter to indicate the parts as well. Application for dual dimensioning. We are going to use both customary and metric units. It permits the manufacturers of parts in either unit of measurement. So if you are given a print and you need to build it to either inches or you need to build it to millimeters, you can off of that. This is more important for machinists because machines that build these parts track at different rates. So a lathe or a milling machine can be tracked in its gearbox to work with decimal fractions or fractions for US customary, and then it won't be able to make millimeter. So you need to be able to adjust that and find the equivalent US customary, or if you're working with a lathe that's set up for metric system, you need to have the US customary equivalent in millimeters to work with that. This is more of an issue whenever it comes to international prints. It makes it easier to facilitate manufacture all over the world. So if you only have your US customary sizes on your prints, you can only build them in shops that can use customary inches or that way. Now, if you want to go international, most other countries use the metric system. I believe there's only 3 countries in the world that use customary, and the US is one of them. Now, dual dimensioning can be expensive because it takes up more room on the print and it takes more time to actually convert all that and make sure they are converted correctly. But traditionally, you're going to have the US decimal fraction, and then below it, you'll have it in millimeters and brackets, or you'll have it to the side of it in brackets. So the first measurement you'll read will be in US customary, and the next measurement you'll read will be in millimeters or whatever metric dimension that you're using. All right, so the purpose of dimensions are to give the sizes needed to fabricate the part and to indicate the locations where components of the part should be placed. And tolerances will ensure fits of the parts. And scale size is in direct proportion to the size of the object, whether you're using a reduced or enlarged scale. And the 2 methods of dimensioning we'll be using are conventional dimensioning or baseline.